For more than 5,000 years, Longaví Volcano in Chile had remained almost completely silent. No recorded eruptions, no major signs of unrest, and no obvious indications that anything unusual was happening beneath its slopes. But then, within just a matter of days, everything changed. More than 400 earthquakes suddenly began striking beneath the volcanic region, prompting monitoring agencies to raise the alert level and establish a restricted zone around the summit. What caught the attention of scientists was not only the sheer number of earthquakes, but also how abruptly they appeared after centuries of apparent calm. Was this simply a temporary episode of geological unrest? Or could Longaví be sending the first signals of a new volcanic cycle? As seismic instruments continue detecting vibrations deep underground, experts are watching closely, searching for clues that could reveal what is really happening beneath one of Chile's long silent volcanoes. The story began around May 20th, when monitoring instruments detected the first signs of unusual seismic activity beneath the Longaví volcanic region. At first, the earthquakes seemed relatively minor, the type of activity that can occasionally occur in volcanic areas without leading to anything significant. However, what happened next quickly changed that perception. Located roughly 54 kilometers east-southeast of the town of Longaví in central Chile, this ancient stratovolcano had shown virtually no meaningful signs of unrest for decades. That is why the sudden appearance of a concentrated earthquake swarm immediately attracted the attention of volcanologists. Day after day, new seismic events continued to occur, suggesting that something beneath the volcano had changed. As scientists examined the data more closely, they realized this was not a random cluster of isolated earthquakes. The pattern was organized, persistent, and energetic enough to trigger increased monitoring. Within a short period of time, authorities decided the situation warranted a higher alert level, marking the beginning of a closely watched volcanic unrest episode. As the days passed, the scale of the unrest became increasingly difficult to ignore. What began as a handful of earthquakes soon developed into a powerful swarm consisting of more than 400 seismic events. Most of these earthquakes originated at a depth of roughly 3 kilometers beneath the surface, indicating that the source of the activity was relatively shallow within the volcanic system. Among the swarm were several stronger earthquakes, reaching magnitudes in the 3 and 4 range, large enough to stand out clearly on monitoring networks. Each new event added another piece to a growing puzzle that scientists were racing to understand. The sheer number of earthquakes occurring within such a short period suggested that an active process was unfolding beneath the volcano. Adding to the concern, monitoring stations also detected several long-period earthquakes and a volcanic tremor event. While none of these observations confirmed that magma was moving upward, they demonstrated that the subsurface environment had become unusually active. For a volcano that had appeared quiet for thousands of years, this sudden burst of energy was impossible to overlook. As scientists mapped the locations of the earthquakes, they discovered something unexpected. The swarm was not occurring directly beneath the center of Longaví Volcano, where many people would naturally assume volcanic unrest should begin. Instead, the earthquakes were concentrated approximately 4.5 kilometers southwest of the volcano's summit. That detail immediately raised new questions. If magma were rapidly rising toward the surface, researchers might expect seismic activity to cluster beneath the main volcanic edifice. But this pattern looked different. The earthquakes appeared to be focused along a separate zone, suggesting that the source of the unrest could be linked to deeper structural features hidden beneath the landscape. For volcanologists, location can be just as important as magnitude. Every earthquake acts like a clue, helping reveal what is happening underground. The unusual position of this swarm made the situation far more complex than a simple magma intrusion scenario. Rather than providing clear answers, the data opened the door to multiple possibilities. And as more earthquakes continued to occur, understanding the true cause of the unrest became an increasingly urgent challenge for monitoring agencies. With more than 400 earthquakes shaking the area, one obvious question quickly emerged. Was magma rising beneath Longaví Volcano? In many volcanic crises around the world, increasing seismic activity is often accompanied by other warning signs. Scientists typically look for ground deformation, swelling of the volcanic edifice, changes in geothermal activity, or increased gas emissions. Yet, at Longaví, those signals were notably absent. Monitoring data showed no significant uplift of the ground surface. Instruments also failed to detect any major deformation that would suggest magma was forcing its way upward through the crust. Even the volcano's geothermal system appeared largely unchanged. For researchers, This lack of supporting evidence was a critical piece of the puzzle. That does not mean magma can be completely ruled out. Deep beneath the surface, small volumes of molten rock may still be moving in ways that current instruments cannot clearly detect. However, based on the available evidence, scientists could not confidently point to an active magma intrusion. Instead, the volcano was presenting a more complicated and uncertain picture, one that demanded careful observation rather than immediate conclusions. If rising magma was not the most likely explanation, then what was driving this remarkable burst of seismic activity? One theory gaining attention focuses on Longaví's hydrothermal system, the network of hot water, steam, and volcanic gases that circulates through fractures deep beneath the volcano. Scientists believe that an increase in heat at depth may have altered the pressure within this underground system. As hot fluids move through cracks and faults, they can act as a lubricant, reducing friction and making it easier for rocks to slip. When those faults suddenly shift, earthquakes are generated. This process can produce large earthquake swarms, even when magma itself is not actively rising toward the surface. The detection of several long-period earthquakes and a volcanic tremor event appears consistent with fluid movement beneath the volcano. While this explanation remains a hypothesis, it offers a possible reason for why so many earthquakes occurred without clear signs of deformation above ground. Yet even this scenario carries uncertainty. Changes within a hydrothermal system can sometimes be the first stage of broader volcanic unrest, making continued monitoring essential in the days and weeks ahead. Despite the hydrothermal explanation, scientists remain cautious. Volcanoes are complex systems, and history has repeatedly shown that the earliest signs of unrest are not always easy to interpret. In some cases, changes within a volcano's hydrothermal system have occurred months or even years before magma-related activity became evident. What begins as fluid movement underground can sometimes evolve into something much larger. That uncertainty is exactly why researchers are paying such close attention to Longaví. At the moment, there is no clear evidence that an eruption is imminent. However, there is also not enough evidence to completely dismiss the possibility of deeper magmatic processes developing over time. The challenge lies in determining whether the current earthquake swarm is simply releasing built-up pressure, or whether it represents the opening chapter of a longer period of volcanic unrest. For now, every new earthquake, every seismic signal, and every monitoring update adds another piece to the puzzle. Until the volcano reveals a clearer pattern, caution remains the most responsible approach. The story beneath Longaví is still unfolding, and scientists know that conditions can change unexpectedly. As uncertainty continued to surround the earthquake swarm, authorities decided that caution was necessary. In response to the ongoing unrest, a 3-kilometer exclusion zone was established around the summit of Longaví Volcano. While no eruption had occurred and no direct signs of rising magma had been confirmed, officials understood that volcanic systems can evolve rapidly, sometimes with little warning. The restricted area was not created because disaster was imminent. Rather, it was a precaution designed to protect anyone who might be near the volcano should conditions suddenly change. At the same time, monitoring efforts were intensified. Seismic instruments, satellite observations, and other surveillance tools continued collecting data around the clock. For nearby communities, the exclusion zone served as a visible reminder that something unusual was happening beneath the mountain. Although daily life largely continued as normal, scientists remained focused on detecting any new signs of unrest. Every update mattered, because the next clue could help determine whether Longaví was simply experiencing a temporary disturbance or entering a more significant phase of activity. To understand why the recent earthquake swarm has attracted so much attention, it helps to look back at the long history of Longaví Volcano itself. Rising high above the surrounding landscape of central Chile, this stratovolcano has been part of the region for hundreds of thousands of years. Scientists estimate that volcanic activity at Longaví stretches back at least 613,000 years, making it one of many ancient volcanic systems that have shaped the Andes over immense periods of time. The volcano is composed primarily of andesite and dacite, two types of magma often associated with explosive volcanic eruptions. Over countless generations, layers of lava, ash, and volcanic debris gradually built the mountain seen today. Wind, ice, and weather then sculpted its slopes, leaving behind the heavily eroded edifice that now dominates the horizon. Despite its age, Longaví has remained relatively quiet in recent geological history. That prolonged silence has made the current unrest particularly intriguing. When a volcano spends thousands of years appearing dormant, even moderate changes beneath the surface can attract significant scientific interest. The mountain's past reminds us that silence does not necessarily mean inactivity. Sometimes it simply means the next chapter has not yet begun. Although Longaví has been quiet for thousands of years, its geological record tells a very different story. The volcano's two most recent known eruptions occurred during the Holocene and reveal that this mountain was once capable of producing powerful explosive events. The first eruption took place around 5,650 years before the Common Era, ejecting large volumes of dacitic pumice high into the atmosphere. It was a dramatic reminder of the energy stored beneath the volcano. Then, roughly 1,900 years later, Longaví erupted again. This event produced a growing dacitic lava dome near the summit. Over time, portions of that unstable dome repeatedly collapsed, generating fast-moving pyroclastic flows that swept down the volcano's slopes. These scorching avalanches of ash, rock, and volcanic gases traveled for several kilometers, leaving behind thick deposits that can still be identified today. While official eruption intensity estimates remain uncertain, the evidence suggests that both eruptions were significantly explosive. For scientists studying the current unrest, these ancient events serve as an important reminder. If Longaví were ever to awaken again, its future behavior could be far more powerful than its long silence might suggest. So what would happen if Longaví were to erupt again in the future? At this stage, no one can answer that question with certainty. The volcano has remained quiet for so long that scientists have only a limited record of its recent behavior. However, its past eruptions provide valuable clues about what might be possible. Given the volcano's dacitic composition, any future eruption could potentially be explosive rather than gentle. An eruption might begin with increasing seismic activity and gas emissions before progressing to ash plumes rising high above the summit. If a lava dome were to form again, parts of it could become unstable and collapse, generating dangerous pyroclastic flows capable of racing down the volcano's slopes at tremendous speeds. Fortunately, very few people live close to the volcano itself. Yet, volcanic hazards do not always remain confined to the summit area. Ashfall, fast-moving volcanic flows, and secondary hazards could affect regions much farther away. This is why scientists continue to monitor every development carefully. Even if an eruption remains unlikely today, understanding the possible future scenarios is an essential part of volcanic risk assessment. Perhaps the most overlooked hazard at Longaví is not the volcano itself, but what could happen to the ice that rests upon it. The volcano is capped by a glacier, and during a future eruption, even a relatively modest amount of heat could melt significant volumes of ice and snow. When meltwater mixes with volcanic ash, rock, and debris, it can create powerful lahars, fast-moving volcanic mudflows capable of traveling far beyond the volcano's immediate surroundings. These flows would likely be funneled into existing valleys and river channels, potentially reaching areas located many kilometers from the summit. Some researchers believe the current hazard maps may underestimate how far large lahars could travel under certain conditions. For now, Longaví remains in a state of uncertainty rather than crisis. The earthquake swarm has raised important questions, but it has not yet provided clear answers. Scientists continue to watch closely, analyzing every new signal from beneath the mountain. Whether this unrest gradually fades away or marks the beginning of a longer volcanic awakening remains unknown. For now, Longaví is keeping its secrets, and the world is waiting for the next clue. Subscribe to Weather Today for the latest volcano updates, earthquake alerts, extreme weather events, and breaking natural disaster coverage worldwide.